All right, thank you everyone for coming and welcome to the talk. It's my pleasure to introduce Yo Suzuki. He is a fifth-year PhD student at University of Colorado, and he works at the intersection of HCI, robotics, and UBCom. And today he'll be talking to us about programmable environments with distributed swarm robots. Please feel free to ask questions. Just give him the first 10 minutes to set the context for the talk before you ask your questions.
Great. Thank you for the introduction. Hi, my name is Ryo Suzuki. I'm currently a fifth-year PhD candidate at the University of Colorado, Department of Computer Science. So today, I want to talk about the programmable environments with distributed swarm robots. So my main research interest is situated at the intersection between human-computer interaction and robotics. During my PhD, I've been working on how we can leverage the interactive swarm and the soft robots as human-computer interfaces, and how we can leverage these robots to make our everyday environment more adaptive, interactive, and programmable. So this talk is about to answer that research question: how can we make static physical environments more programmable through distributed swarm robots? And how can we computationally control the physical elements of our everyday environment with the distributed swarm robots? So I'm interested in this research question because ever since I've been started working on a human-computer interaction research, I'm motivated by how we can leverage the physical objects or environments as a means of human-computer interaction. Because today's the computer interfaces are mostly dominated by the graphical user interfaces and a tiny computer screen. So what we can program is what we can change this tiny computer screen, right? But we are surrounded by the rich physical environments, and we have an innate capability of manipulating objects and interacting with the physical environment, which we have developed since prehistoric time. But the graphical user interfaces are so powerful, so they can, just simulate anything like maps, the camera, books, or the typewriter, or the musical instruments like that. So the graphical user interfaces are dominated how we can interact with the digital world. So as we can see, the two worlds are currently divided each other. So the computer cannot really control the physical object, and we cannot also leverage the physical object environments to interact with the digital world. So I'm interested in how we can create the environments, object, and the user experiences which can, where the digital world is seamlessly blended into the physical world. Then the question is how we can make this static non-programmable environment the programmable, and how we can computationally control the elements of this environment. So if you look at the history of the human-computer interaction research, then it can be also seen as a history of the addressing this research question. For example, the Mark Weiser's ubiquitous computing to the Pierre Wellner's digital desk or spatial augmented reality, and Hiroshi Ishii's tangible bits and the tangible user interfaces. So all of this research vision have tried to address how we can seamlessly blend the digital world into the physical world. So thanks to the decades of this research, we are now gradually able to program the environment, right? So for example, we are now living in an environment where we can computationally control the lighting, the heating, or air conditioning, the sound, or the visual property of the environments. However, the physical elements of our living environment are still static and non-programmable, because the computation, in contrast to computationally control lighting or air conditioning, controlling these physical elements, physical property of the elements are still difficult to manipulate. So again, my research question is then how we can make the non-programmable physical environments more programmable. and how we can computationally control the physical elements of these our living environments in a more dynamic and interactive and programmable way. So to answer that research question, I have been working on using distributed swarm robots at the various scales as a means of making a physical environment more programmable. So that these custom-built the swarm robots from the fingertip size to the room scale size can, dynamically construct the shape and collectively actuate the objects, and dynamically interactively reconfigure the environment in a more programmable way. So these robots can be easily deployed into the existing environment so that we can make our environments more adaptive, interactive, and programmable. So in the literature of HCI, there is an emerging research topic about programmable shape-changing interfaces. So again, today's user interfaces has been dominated by the graphical user interfaces. But the shape-changing interfaces has been working on how we can leverage the dynamic physical object as a computer interfaces. So this kind of the research is started from the special purpose shape-changing interfaces, but they're gradually shifting to more like a general purpose shape-changing interfaces by leveraging the so many actuated elements. So for example, this one is Inform, developed by MIT Media Lab. So this system are trying to program not only the pixel of the computer screen, but more like the program the physical surfaces to embrace the digital computation so that it can actuate the object, construct the shape, or be present the human hand in a remote way. By the way, he is my advisor, Daniel Leitinger. So these systems are pretty cool, but these systems often require a large, mechanically complex devices, something like that, and then which can be often difficult to deploy into the existing environment. So in general, if you plot the existing work, then this system going to the general purpose, then it's going to be required a much more complex, gigantic system. So I'm interested in then how we can increase the deployability of these general purpose shape-changing, general purpose dynamic interfaces, but while maintain the general purpose programmability. So I believe distributed swarm robots can be a pretty, one of the promising approach to achieve this goal, because the distributedness of these swarm robots can be easily deployed into the existing environment, but also the swarmness or modularity of these robots can, can be used for the many applications. So that, for example, this robot can collectively and autonomously deploy and move on a transform in an existing environment, we can probably achieve this goal. So that's one of the motivations that I'm taking this approach. And also, I believe we are standing at a very unique and exciting moment in the history of robotics. So in the history of computers, the computer used to be a very gigantic, mainframe computer. But as the computation becomes cheaper, the smaller and more powerful, we are now living in an environment where the hundreds of computers are surrounded and distributed in a single room. So I believe the same thing is happening in the history of robotics. So the robots are also now they're pretty gigantic and only work within the factory or warehouses, but they are gradually migrating from the factory into our everyday environment. And I believe the robots are also ubiquitous in the next 20 to 30 years. Then the question is how we can interact with these robots and what kind of application can be possible. So for example, imagine to think about the future where robots are almost equivalent to today's IoT devices, and that we are living in an environment where hundreds of robots can commonly support our everyday life. So then the question is how we can interact with it and how these robots can support our life. So this is how I contributed as an HCI researcher. So as an HCI researcher, I have contributed to illustrating the potential future or the potential application enabled by these swarm robots, as well as develop the interaction technique with these swarm robots. And also identify the challenges from the both technical and the user interaction perspective to which we need to solve today. So in this talk, I want to introduce my work to illustrate this potential future. So during my PhD, I have explored the application that range from using these swarm robots as an everyday assistant to using these swarm robots to the tangible interfaces. So for example, one of my work is using these swarm robots to provide physical affordances to augment our everyday environment. And these swarm robots can also reconfigure environments by rearranging furniture. Or these swarm robots can make data or information accessible for blind users. And these robots can also construct a shape to make an object which we can interact with the digital world. So this work, my contribution in my domain, and Kai and Width is my, the two major fields in HCI. So, okay, now I want to talk about the first project called the ShapeBots. So the ShapeBots is shape-changing swarm robots that can move around on tabletop surfaces so that they can collectively and individually transform its shape to represent the data for data physicalization or actuating objects or the construct the shape for the everyday purposes. So the ShapeBots is inspired by the recent research topic about the swarm user interfaces. So the swarm user interfaces is trying to leverage swarm robots as computer interfaces. But most of the swarm user interfaces and the swarm robots in general have limited capability about the constructing a shape or their functionality because they cannot individually transform its shape. So in this project, we are interested in what if these robots can also change its shape, and also collectively change the shape so that for constructing a shape or actuating an object or representing data. So we are interested in how this kind of individual and collective shape transformation capability can enrich the functionality as well as the expressiveness of these interfaces. But to enable that, we have technical challenges. Because the swarm robots are so tiny, so the technical challenge is how we can make a miniature actuator that can fit into the small form factor, but also have a large transformation capability. So to do that, we have developed the miniature reel-based actuator, which is kind of inspired by the tape measure. So the tape, as you can see, the tape measure, it's pretty compact, but it also has a kind of large deformation capability by rotating and extending this kind of the reel. And then they are putting this kind of the modular actuator on top of each swarm robots, so that these swarm robots can not only changing the shape in a horizontal direction, but also the vertical direction, or the using as a curved line, or attaching an origami to expand in the 2D surfaces of volumetric change. So then the question is, what kind of application we can use it for? So we have identified the 4 different categories of the application. So for example, the first one is object actuation. So these swarm robots can actuate the object, for example, the dust in the desk, so that they can clean up before the user is starting using it. or they can, institute, the providing a tool whenever you use. Also, this robot can be used to provide physical affordances. For example, if the coffee cup is too hot, then these swarm robots can gather together to make a vertical fan, so that to indicate you shouldn't touch because it's too hot. But once it's ready, this robot can disperse and disappear into the environment. So these robots can kind of augment the existing environment to provide, the physical affordances. And also, this robot can be used for the displaying information, like, for example, the sign curve, or this one is showing the population data for each state, so that we can see and touch and interact with it, or the construct shape, or showing the character. So we submit it to WIS, so why not? And also, we can use it for physical interactive, tool. So to synchronize between the digital world and the physical world. Like, for example, if you're working on a CAD software, then these robots can not only show the output, but also use as an input tool. But also, these robots can themselves become a tool, like a ruler, for example, in this case. So these robots can, become provide a tool, on demand. So these are kind of the 4 different categories how we can use these swarm robots for everyday assistance. So these swarm robots can deploy and blend it into the environment so that they can naturally augment our existing environment. But we are also interested in how we can, not only move on the tabletop side, but also in the scale up to the larger scale. Because we are interested in, how we can scale it up to not only to reconfigure the object within the tabletop side, but we are surrounded in a, large object in like a space like that. So how we can actuate or reconfigure the environment at a larger scale. So to do that, we have developed shape-changing swarm robots that can rearrange the furniture. So that these swarm robots can go underneath the table or the chair or the furniture and pick it up, and then they lift up and move to rearrange the furniture in a more programmable way. So particularly, this approach is interesting because when we try to make the environment more programmable or interactive, the typical approach is to hack the existing chair or existing table by attaching a motor or actuator. But these robots can adjust the height and lift up any kind of common standard furniture so that they can actually deploy into the environment, and then they can naturally adapt to the environment. So that, for example, these robots can move this kind of standard common furniture we have tested. And then there are so many application domains, I think. Like, for example, using as a spatial reconfiguration for adaptive environments. Like, for example, if you press a button, then this robot can immediately reconfigure the space by rearranging furniture from the meeting space to the kind of interview space or kind of the discussion space based on a calendar event, for example. But also, we can use it to provide haptic interfaces for like augmented reality or virtual reality to match between the virtual world and the physical world. So in this project, we specifically explore the second application domain. So the idea is, in a virtual reality, we are in a scene, virtual scene, like the new room, a new office you are designing. But this kind of virtual object, we cannot see, but we cannot touch, interact with or sit down on it. So the idea is, what if we can reconfigure the physical environment to synchronize the virtual world and the physical world, so that we can also, not only see the virtual object, but also can touch the object. So in this way, so this swarm robot can continuously, rearranging the spatial environment. So whenever you work or whenever you teleport, then this robot can construct, the physical space based on the virtual reality. So that whenever you see that there is actually kind of physical object, physical chair or physical desk you can touch. So there are several, interaction techniques. Like, for example, if you teleport in a virtual scene, then this robot can construct, reconfigure the scene, the physical environment around you to match to the virtual scene. As well as you can use it for, if you virtually edit the scene, then they can also physically change the scene. As well as using the locomotion capability of these robots to mimic a larger scale, of the desk to to provide a visual illusion for that. So this is actually how we build. And the good thing of that is that it's pretty low cost and easy to make. So it's actually the Roomba, and we attach the laundry rack we bought in the Target. And then we attach on with a linear actuator to extend it. So the nice thing about it is the research prototype is usually kind of become useless after the project, but we can actually use it as a laundry rack at home. Right? And it's also the programmable, so we can actually program the laundry rack to continuously change the sunlight, at home or something like that. And then we are using a retroreflective marker and motion capture to to track the robots as well. So the scissor structure can extend from 20 centimeter to 100 centimeter. And then we also attach to the retroreflective marker for the furniture as well. So we can continuously track the position of both the robots and the furniture. So again, this one is one specific application domain about how we can use these swarm robots to reconfigure the environment to match to the virtual scene. But we are also interested in how we can deploy into the environment to reconfigure the environment. So these two are more like how we can use it as an everyday system. So there is no, but we are also interested in using these swarm robots as the tangible interfaces or the tangible medium that we can interact with it. So the next project that I want to show you is using these robots to make the data and the information accessible particularly for blind users. So this project started from the 3D printed picture book project led by Professor Tom Ware, who is one of my advisors. So this project, we are trying to make the picture book tangible for blind children, because the blind children cannot read the picture book, but they need to touch the information to read it. So the idea is how we can make the picture book more tangible so they can touch the information, touch the book to read it. So typically, to do that, we often use the tactile graphics like this, using an embossed paper to make a bump to draw graphics on top of the paper. But these tactile graphics are static, so it cannot embrace the dynamic content on top of it. So, for example, if we are interacting with the tactile maps, then if we want to kind of ask a question like, where is the nearest coffee shop around here? So if you interact with the graphical user interfaces, it's so easy to program the dynamic content on top of it. But in the physical, the static graphics, it doesn't have any capability to dynamically, change the content. So the idea is, what if using this kind of tiny swarm elements to point out the location when you ask the question like, where is the coffee shop? So that these objects these kind of swarm elements can point out the location so that they can embrace the dynamic content, and they can also touch the information through it. So to enable that, we have investigated several different approaches. So one of which is obviously kind of pin-based approach or kind of off-the-shelf kind of swarm robots like that. But for blind users, these kind of objects are pretty big. Like the swarm robot cannot be smaller than 3 or 5 centimeters, but they need to touch like a more precise location, like a millimeter scale. So one of the promising approaches is using electromagnetic coil or an electromagnetic force. So because using a passive magnet, so we can scale it down to the millimeter scale. But one of the questions is the cost and the scalability, because this one is from the Pico of the patent and Hiroshi Ishii, but they need to construct a crazy number of the coil to actually construct the electromagnetic coils. So one of the contributions we had is using a PCB, developing a PCB-based electromagnetic actuation. So having a coil for the 4-layer coil with the PCB, then the running current the coil through the coil for each coil, then generate an electromagnetic force to attract the magnets nearby location. So by sequentially turning on the coil, then we can actuate in any arbitrary X and Y position, something like that. And it's also pretty thin and scalable. So I already have here, but it's pretty thin, and we can also scale it up to the larger to cover the larger display. And it's also pretty cheap compared to the manually constructed shape. And it also you can also actually kind of order to Shenzhen and get this board in 2 weeks, for example. So it's pretty the accessible way to do it. So there are also several different applications, like spatial navigation to data analysis or guided drawing, and we have we have a user interview with 6 blind people to identify what could be the potential benefits of that. So they are pretty appreciated about the low cost and the large scale size of the display, because the refreshable braided display often becomes a small size. So it cannot embrace a larger display. But also the mobility can increase independence, so they can bring it to whenever they go. And also, particularly, they are excited about they can bring it to the classroom, so that making the learning or more the accessible or adaptive based on the like a synchronized between what the teacher says and what they can see. So this is the kind of the third category about how we can use the swarm of the actuated elements to make the data and the information more accessible. But all of these kind of swarm elements are only capable to move on the 2D surfaces. But how we can go beyond the 2D, like how we can construct and assemble the 3D shape out of it to make an object that we can interact with. So when I think about this idea, I made some kind of concept video with stop motion animation. So for example, you can grab an object out of the computer screen, and then you can also, so these are kind of physical objects, so you can actually interact with it. And then these objects are also digital, digital things, so that you can seamlessly integrate between the digital world and the physical world. So this is the kind of idea what I want to make. And the think about it, and then we have an idea about how we can make it. So this is the kind of idea. So we have a kind of pin-based display, and we're gonna stack the blocks on top of it. Then the actuating pins to push up these blocks. By the way, here is the kind of actual blocks like that. But then they construct layer by layer to create the kind of arbitrary 3D shape. And these 3D shapes are also made of the blocks. So if you press down to the ground, then it's going to be reusable for the next iteration. So to make that, we have first tried to make the kind of pin-based linear actuator. So these are kind of the motor for each column. And then we made a kind of 24 by the 16 to actuate the pins. And then place the stacked blocks on top of it so that this pin can push up from the bottom to construct the shape. And for the block, we used a 3D printed block, 3D printed blocks, and embed the sphere magnets on inside it. So the blocks can connect and disconnect in horizontal ways. And then by pushing up selectively, computationally, these blocks can come up from the surfaces to make a object layer by layer. So for the trick for the disconnection and connection, we use the spacer between each blocks, so that this spacer can prevent the magnets from connecting each other. But once we push, then this spacer is going to be gone, so that the magnets can connect together. And then using weaker magnets for the vertical direction, so that we can push up, and then we can construct a kind of overhanging structure. So in this way, we can dynamically construct and assemble arbitrary 3D shape, just like a 3D printer. So, for example, here is the real-time, the video, and you can see that these objects are, assembled by pushing up the pin, and it can also create an overhanging structure, like a miniature table like that. So, for example, the architects can dynamically construct this shape without waiting for an hour of the 3D printing finish. This object can also, they are reconstructible. So if you push it down, then you can make a new object out of it. Again, it's also, the dynamically programmable. So, and a layer-by-layer approach can make arbitrary 3D shapes. So we can also make a kind of low resolution stuff for the money like that. So this is the how we can use the swarm of elements to not only move on a tabletop, but also to construct the shape out of it. So we can use these swarm robots to provide physical affordances. These swarm robots can also reconfigure the environment by rearranging furniture. But these swarm robots can also make data and information accessible for blind users, and these swarm elements can also construct through the to make a shape. So these are kind of four major projects for the the main contribution. How we can leverage the distributed swarm robots for everyday environment assistant to tangible user interfaces. But the robots, the definition of the robots are also kind of expanding recently. So from the mechanical robots to recently kind of soft and pneumatic-based robots are kind of emerging in the field of the robotics, and as well the HCI. So in other research highlights, I've been also developing the modular soft robots and inflatable actuator for the shape-changing interfaces. So for example, the first one is about the Morpure. So in this project, we developed the novel entirely soft sensor, sensing and actuation module for the soft robots that can sense the deformation as well as actuate it. So in this module, we have a conductive sponge sensor in it so that they can sense the deformation. So if you deform it, then they can memorize the motion. And in the same way, they can actuate the same motion to, like, for example, the programming by demonstration of the soft robots. So again, this module can, dynamically sense the deformation, so we can propagate the change. So this is how we can measure the deformation. So using a conductive sponge to measure the resistance between bottom and top to, to see the deformation, to sense the deformation. So interesting application is these are kind of soft and adaptable to the environment or object, so that we can attach to the stuffed animal to the dynamic and remotely kind of control or the prototypes motion of these robots. These are also kind of modular, so we can quickly prototype the soft robots to construct a new geometry, and we can also kind of prototype this by coding, not coding on the screen, but programming through the tangible interactions. And also, this one is we published to the TEI recently, that using a pneumatic actuator to make a modular, the room scale shape changing interfaces. So, for example, using the plastic tubes to inflate the object, the object, but also they're using constant force spring to naturally, retract the actuator. So it has kind of 20 centimeter by 20 centimeter, and using the air supply and the air release hole to by supplying air to extend it, and also the retracting with deflating. Again, it's also the modular, so that we can easily combine to the horizontal direction or the vertical direction, so that we can combine it to the kind of to these 1D surfaces, or we can also dynamically, the extend in horizontal surfaces. So, for example, one of the applications could be like using this the object to provide haptic interfaces for virtual realities. And also the interesting thing is that this is a compact, so we can make it in a horizontal direction to provide a kind of shape-changing wall. So, for example, these are kind of showing a character. We submitted to TEI, so why not? And then they are showing like an arrow shape to construct these kind of their room scale size. So we are proposing this more like a prototyping environment, prototyping tool for the room scale shape changing interfaces. But again, these are kind of pretty kind of low cost, the scalable approaches. We are also interested in how we can combine the material sides of this actuation to make it more environment more dynamic and interactive. All right, so here's the summary. Again, so my research question is how we can make the non-programmable, this physical environment, more programmable. So how we can computationally control the physical elements of these, the everyday environments more programmable. So to answer that research question, I've been working on using a distributed swarm robots at various scales, from the fingertip size to the room scale size to make everyday environment programmable. So these swarm robots can collectively, actuate the object, construct the shape, as well as reconfigure the environments for human-computer interaction. And I'm also taking this approach because, again, I think this is a pretty promising approach to make the interfaces more deployable to our everyday environment, while maintaining the general purpose programmability of these swarm robots. So here are the main 4 categories of what we can do, what we can use it. So we design the application and the interaction technique through providing affordances to rearranging furniture for accessible purposes, and provide dynamic, the shape construction. All right. So let me briefly talk about the future work and the future research directions. So again, my research vision is to, in the next 20 to 30 years, the swarm robots are almost becoming more like IoT devices today. So these swarm robots can embed it and distribute it into the everyday environment. Then these robots can, seamlessly blend it into the environment. So in my previous work, I have tried to develop the proof of concept prototype to envision this kind of future. But if we really want to deploy into the real world environment, we have so many aspects of the problem we need to solve today. So for example, like a software, the problem, a software aspect, and a hardware aspect, and a programming aspect, and the user interaction aspect. So for example, for the software aspect, we need to have the better, robust, and easier to integrate the tracking system, as well as the scene understanding system, scene understanding capability. Because compared to the factory, our everyday environment more like a messy. So we need to have a better understanding of the scene and how the user interact with it. And talking about the hardware, these robots are, running a battery in an hour. So it's very, frustrating for the maintenance. So how we can solve it. As well as these robots can only move around on top of the surfaces, then how we can make it more, the robots can climb up on the wall or moving on the ceiling. And the programming aspect is about, these robots are mostly the central control, but how we can program these robots in a more distributed way. As well as the end user programming aspect of these swarm robots are also interesting. And finally, the user interaction aspect, we need to better understand about how the people react with these swarm robots and how they, interact with it. So particularly about the first topic, so we have been using the kind of easier way to deploy because our main goal is to make a proof of concept. For example, we use using a fiduciary marker on the bottom of the robots, or using a motion capture system, or sometimes using computer vision. But these are more like not very robust, as well as the costly tracking system. So how we can solve this kind of tracking mechanism problem. And also the human-robot interaction aspect is how we can better communicate with these swarm robots. So for example, sometimes like Roomba robots is somehow very dangerous in the sense these robots can immediately kind of relocate a chair if you want to sit down. So that we may probably need to have better channel to communicate with these swarm robots. So one of the projects I have been working on is with a colleague at my university, which is, for example, using augmented reality to see the intention or see the path of the drone. So for example, in this case, the drone are also pretty dangerous, but by showing the path with augmented reality, we can see where these robots are going. So it's somehow interesting to how we can leverage the augmented reality to better communicate and better support the understanding between the robots and the human. And also how we can make the programming a little bit more distributed in the sense of the user interaction perspective. So each swarm element can have a state or the program, and then we can combine it to make a new state, for example. So these are kind of a point-wise future research direction. But if we think about the design space of the existing swarm robots that I showed you, is probably the design decision between whether we offload the capability to the environment or we can embed into each robot. So for example, like a computation and a communication, or sensing or tracking capability, or actuation, or the power supply, or connection or disconnection capability. So for example, think about the Roomba robots, like a reconfiguring robots. So we can see the computation and the communication on the central, and using a tracking mechanism by using environment-based tracking. But if we think about, for example, using a simultaneous localization approach, like a swarm-based approach, to attach the camera for each robot to make more, increase the deployability. As well as it's also somehow interesting to see how we can also, not for the central control, but also make the program to the distributed to the each robot, so that they can work more kind of scalable way as well as the autonomous way. And for the shape mods, we are currently, each robot has a battery. But what if we can use the wires power transferring to reduce the size as well as the maintenance-free swarm robots? So we are actually, collaborating with the researcher at the University of Tokyo to trying to, achieve it. As well as, what if these robots can also not only the move around, but also the connect together to make the graspable robots out of it. And for this one, so most of these capability, so these blocks are only having capabilities to connect and disconnect. But what if we can embed the tiny tiny sensor into each robot, so that each element, each block, so that the block can sense how the user is currently constructing a shape. Also, for this one, we can only actuate the magnetic object because they're using electromagnetic force. But we are interested in what if they're using a vibration-based actuation, like a piezoelectric actuation, to actuate any arbitrary shape on top of the table, so that we can not only actuate the magnetic object, but also any kind of objects. So these are kind of the research in the direction I'm interested in, and this is also kind of research, the design decision, how we can offload the computation or communication or actuation power supply into the environment or each swarm robots. So there are kind of rich space how we can augment this kind of work. Again, so this is the kind of the research vision. So in the next decades, we are trying to make the robots almost equivalent to the IoT devices today. So we can surround it by the robots, and then the question is how we can interact with these swarm robots. So through my work, I tried to make the proof of concept prototype, but actually making these swarm robots truly ubiquitous and autonomous, we have so many the problem we need to address, which I'm very excited about working on the next 5 to 10 years. So for the long term, so these swarm robots can only interact with the existing environment to make our everyday environment more programmable. But another way of the direction is there is also the concept about the making the object out of this robot. So the robot itself could be a kind of material. Like so, the programmable matter approaches has been working on like 50 years now. But I think the swarm robots approaches is somehow they can cover both sides, because they can also actuate, reconfigure the existing environment, but they can also correctively move to make a shape. Like for example, in Disney's The Big Hero 6, so these are kind of the dynamic object out of the many thousands of the swarm element. So I do think the swarm robots approach is not trying to solve the problem today, but also the towards the 50 years from now to the Ivor Sutherland ultimate display. So Ivor Sutherland, who is the founder of the augmented and the virtual reality, once wrote the ultimate display would be, of course, be a loom to computationally control the existing matter. So I think we are also working toward this vision that not only for solving the problem today, but also this project could be going towards programmable reality to make the environment truly dynamic and interactive and programmable. So finally, I want to thank my collaborator and advisor and assist committee. Without the continuous support with them and continuous interaction with them, so it was not possible. So I really thank particularly the Daniel Light Engineer Macros and Tom Ye and Hiroshi and Takeo Igarashi for the continuous support to make it happen. So this is my work. So thank you for listening, and I'm happy to take any questions.
We have time for a few questions.
You mentioned maybe using AR for. So I have a question.
Oh, yeah.
So you mentioned maybe like using AR to try to follow, like show to the users the path of the drone. But kind of more generally, what's your take on how can we design these environments in a safe way, such that if people mistake how to program the swarm, or it just interact with the world in some way, that kind of the environment remains safe.
Yeah, so no, actually the safety is one of the biggest challenges we have, and then we are so your question is not only leveraging augmented reality, but making a robot itself safe for the many people. Yeah, that's an important question, and so maybe it's definitely a combination with the machine learning, like a software, the software augmentation. Like for example, using the camera or using camera, attaching a camera onto the robots, or attaching a camera in the environment to continuously track the position of the robots, and the people. But one of the challenges is it's becoming a little bit difficult to continuously survey, continuously monitor with the camera for the for everyday environment because of the privacy. So maybe it would be very interesting to think about the different approach, like for example, like I don't know, the thermal sensing or something like that. So this is I think the kind of the research challenge we need to solve. But it's definitely the combination with sensing and the machine learning to make it smarter.
So usually when I use applications, I only need to know a handful of metaphors that work across many applications, so I can effectively get them to do what I want. Across these projects, was there some sort of small set of common metaphors a user might learn to control in all these different applications?
You mean
is there sort of a language of interaction that's emerging as you have more and more applications?
Oh, I see. So I see. That's an interesting question. We have we didn't develop the umbrella, the interaction, the vocabulary to across the project. So we can identify the kind of technical challenges to across this project, but no, to short answer, we haven't investigated so much, but yeah, that's a really good question.
So thank you for the talk. Super creative. The key question I have, and I think you articulate this vision of 20 years out, 30 years out, we have swarm robots all around us, like we have IoT devices all around us. So what is the value proposition? Can you help me understand like 2 or 3 key, societal level problems that might be addressed through swarm robotics?
Oh, that's so one obvious way to use swarm robots is probably, I think, starting from the automation aspect, like a home automation. So that we could probably have, there are so many kind of the labor-intensive, how to say, labor-intensive tasks that we need to actually use a human to move or actuate it. So I do think that would be somehow very the important aspect, like the people would want to need like immediately from the social aspect. So I do think the starting from like a home, or maybe leveraging for like a factory automation thing would be the very first step. But another thing is to let's say social aspect. Yeah. So so one aspect, so one is the home and automation aspect, but another one is we also gradually need to have the physical objects we need to interact, because we are gradually the computation is becoming gradually out of the computer screen. Now we are having like a virtual reality or augmented glasses. But we need to have a gradually better input devices to interact with it. So I do think it's also the kind of the growing needs how the society can provide can leverage these robots for.
All right, let's thank the speaker again.